here, and thanks for having me at GOTO Berlin. My name is Ray. I'm a developer advocate for the Google Cloud Platform. There are two things that I do mostly. Number one is to bring some of the latest and greatest technology that Google has to offer, both on Google Cloud and in open source, to developers all over the world. But I also like to make sure that we have one of the best developer experiences and work with the products team to make the developer experience better. For that reason, I also started the project called Spring Cloud GCP. It's one of the easiest way to try Google Cloud with Spring and Spring Boot with the starters that we have. I'm also a contributor to some of the open source projects, including JHipster, an awesome application generation tool, and I have my own project called JTFert. Anyways, if you have any questions, any feedback about this session, feel free to contact me on Twitter at Satanism. And if you need to get more information with all the sample code or the examples that I am showing today, you can check out my website at satanism.me. Okay? So today, I'm not going to talk about the theories of microservices or whether you should be doing it or not. Right? You should make your own choice by understanding the architecture and its benefits and its issues, and hopefully you made the decision that will solve your problem and not necessarily generating more problems, right? How many people here have already decided to go with the microservices architecture? Okay, quite a few people. Okay, yep. So hopefully, that's going to help you solve your problems as well. But one of the first things that you're going to see when you, say, move into a microservices architecture is that rather than having a traditional monolith where you have one application and multiple instances of that one app to manage, now you have multiple services that you have to manage. And every single one of these services you have to deploy multiple times. You need multiple instances. And the number of instances you have to manage will just increase by a lot, right? And so one of the first problems that you're going to see, of course, is that you need a way to deploy and manage your applications. You need to be able to deploy hundreds of instances potentially onto a whole cluster of machines. Traditionally, like in Java applications, we typically deploy one application server per machine. But with these microservices, with hundreds of them, you won't have hundreds of machines to run it. You'll have to find a way to potentially bin pack them onto fewer and fewer physical resources. And now you have to share the resources with multiple instances of your app. Right? So then you have to deal with isolating the CPU usages and isolating the memory usages so that they don't step on each other's toes. And then if some of these instances goes away or have issues, you need an automated way to restarting them. And of course, you have to deal with the networking of all of these as well. They can be complicated. However, thanks to some of the toolings, we can actually deal with the deployments really easily today. If you are using a platform as a service, that's a very easy way to do it. Just deploy the code, and the platform as a service will help you scale them out. But you can also do it with containers and container orchestration. And Kubernetes is one of the projects that was open source a number of years ago. And now that's like almost a de facto way for people to manage their container deployments at scale. The way that you do it is by declaring a configuration saying that what it is you want to deploy and how many instances you want, and then declare the ways you want to check for the health of this application. And Kubernetes will take care of the rest for you and deploy this onto a cluster of machines. And at a high level, this is how it works. So first of all, you containerize your application, right? You push it to a centralized registry somewhere so that it can be downloaded from all of the other machines in your cluster. The configuration that you write will be pushed to a Kubernetes master node. It will be stored as a document in a key value store or something like that. And then behind the scenes, there is a scheduler that's going to basically run a loop where it's going to check whether the desired state that's been configured in the file matches the actual state that's actually running on the machines. And if it's not the same, then the scheduler is going to say, oh, you need 2 instances, but there's 0 running. I need to run 2 more instances. How do I do that? It's going to ask the machines where you can actually run it. Do you actually have enough capacity, right? And if you do, it's going to instruct that machine to download the container image and start the instance. Right? All of these things are already done. These are ways that we are able to deploy and manage our microservices today. The most important thing here, though, I want everybody to take away, is that through the eyes of Kubernetes, when I want to do this deployment, I have a desired state, and I'm using a well-defined document, basically using nouns and terminologies that Kubernetes understands, I'm writing it down in a file, which I can check into Git or a source repository. Through the eyes of Kubernetes, when I'm deploying this, I'm dealing with the entire cluster as one single unit, but not individual machines, right? I'm also using these well-defined types and APIs to declare my deployment that abstracts everything else away at the infrastructure level. So I'm dealing with the terminology at the Kubernetes level, but if I need to deploy a load balancer, rather than figuring out which actual load balancer I want to use, I can just define and use the name of a service that is well-defined in Kubernetes, and behind the scenes, a plugin or a scheduler, a controller, will actually turn that service into a real load balancer. And because of that, it doesn't matter which cloud you're running on, which physical infrastructure you're running on, you can deal with the application level stuff with Kubernetes in this well-defined API, and behind the scenes, we will make it into a reality. And that is the abstraction of the infrastructure. However, I want to go just a step beyond that and say that Kubernetes, if you really think about how it works, it's almost like a, I have to say it, but it's almost like an ERP system or a content management system, so you will. The document that you write, imagine if you are in an ERP system, you would say, hey, I need to order 2 widgets, and you enter that record into your system. That's your desired state. And behind the scenes, somebody will actually say, oh, I need to order 2 widgets. Let me go ahead and figure out how to get those 2 widgets, buy it, and then ship it to the warehouse, and I'll update the record and say, it's done. It's very, very similar in Kubernetes if you think about it this way. You have a resource definition that is the well-defined nouns and APIs that Kubernetes has defined that defines the desired state. I need to have 2 instances of my app. You push it into the Kubernetes system, document is stored. Rather than having a physical person to making it into a reality, you have a controller, a script, or an application that is just listening for these document requests and then pushing it and making it into reality, right? And I want you to keep this in mind, basically, for the rest of this talk, because this resource definition and the control loop that's running behind the scenes and making things into reality, it's really, really important for everything that you do within Kubernetes and everything that we're doing with Istio, and or if you move up the levels of abstraction in the future about Knative, okay? So the other things that you're going to run into, besides deployment, of course, is that now rather than having the your application and potentially libraries to be able to communicate in memory, and now you have to communicate across the network. And of course, when you're communicating across the physical network, you run into a couple of issues. Well, number one, you need to figure out what language you want to speak between the services. And this is a trending thing for the past 15 years in distributed systems, right? First, we had the binary protocol with, RPC and RMI, and then we had something like XML and SOAP, and then now we have REST and or JSON over HTTP. And of course, every time we have something new, there's something not so good about it, right? And now we're kind of seeing a shift back into RPC because it potentially can be more performant. At Google, the language that we use is called Stubby. It is a binary protocol that we use internally, but you can also find the open source project for it, which is gRPC. Within Google, we do 10 to the 10 RPC calls per second. So we needed to make sure that the language that we are speaking between the services are as efficient as possible, right? But the other problem, of course, is that now you're bound by the physical limits of your network. And it's probably nowhere near the speed of light, for that matter, right? We have to deal with latency. It's not going to be in-memory process anymore, so you have to wait for the response to come back. You have to wait for the serialization and deserialization of your data. And also that you need to figure out how to load balance to the back end. You need to, if the back end goes away, you're going to handle the failures of those things as well. There's just so many potential issues that you could run into with networking. Now, on the topic of load balancing, though, for the longest time that I have been working in the enterprise companies, load balancing had always meant only one thing for me, which was round-robin load balancing, right? Every time somebody says, set up a load balancer, we set up a round-robin load balancer. But is that actually the right load balancer to use? One thing I never really thought about until I joined Google was that what actually defines the load, right? Is the load per request, or does the request actually generate more load? So some requests might generate small load, and some requests might generate bigger loads, right? So it's something that you have to really think about on how you actually want to deal with load balancing. And then now we also have the question of whether you use client-side load balancer or server-side load balancer, okay, or a proxy load balancer. Basically, in the past, I think that I don't know if anyone here went through a service-oriented architecture where you have an ESB set up in your organization. Anyone? Yeah, or not anymore? Not anymore? Yeah. So basically, sometimes you may have to route all the traffic to a centralized proxy or some kind of proxy, and then the proxy will handle the load balancing for you. Or sometimes you need to do the client-side load balancing because you want to avoid the extra hop to the proxy, right? However, there are always pros and cons to either approach. If you're doing a client-side load balancing, what that also means is that you probably will want to have full control over the client, because if you ever want to shift traffic from the client from an old service to a newer version of the service, how would you actually do that in a client-side load balancer? You have to somehow update the registry, or you have to reconfigure the client-side load balancer in the application, and then you got to do the rollout on these client-side applications in order to take advantage of the new services. However, that's not always possible if you don't have full control, in which case you really have to think about just server-side load balancing and how do you scale that, right? So there are a lot of different issues you have to consider beyond deployment, which Kubernetes can take care of for you. Another thing about microservices is now you have server services. Maybe you have some code chaining, so A is calling B, calling C, calling D, or something like that. And if anywhere along that chain has a latency issue, has a performance issue, or has some kind of outage, you need to know and pinpoint exactly what that issue is. Otherwise, the problem will propagate back up to the top, and it will be very, very hard to figure that out. And for that reason, you need some kind of way to observe the state of your entire architecture. And in most cases, documentation is not enough, because documentation is usually outdated by the time you write it, or that a couple months later is not exactly how your production environment works. So somehow you need a way to see into it. Now, for the Java world, there are many, many open source tools to do some of these things, to take care of these cross-cutting concerns, right? And these are some of the popular tools, especially the Netflix OSS stack. So for example, for client-side load balancing, we have Ribbon. And in order for the client-side load balancer to figure out which backends they have to either register or get the data from a centralized registry. In this case, maybe Eureka or Console or something else. And then for handling failures of your request, you have something like Hystrix that does the circuit breaking. And then for observability, we can trace our requests throughout the entire life cycle of that. And then we can store the traces in Zipkin or Jaeger, and so on and so forth. And there are many, many open source tools that we can use. However, some of these tools you have to put directly into your microservice. So your service, in addition to the business logic that you have to handle, which should be somewhat like a single unit, is probably very small, hopefully. But however, you also have to add all of these client-side logic in order to deal with some of these cross-cutting concerns. And now your microservice may not look so micro anymore. It actually become potentially a microservice, right? Even though you're just writing the small piece of the business logic, but in your application, you're actually dealing with all of these cross-cutting concerns. And then you also have to run and manage all of these other components that makes the whole architecture work, right? So you may have to run a gateway in the front. You need to run Grafana and Prometheus and service registry and so on and so forth. And all of a sudden, you're just to run a few services, we're looking at many, many more that you have to run surrounding these services in order to make that operationable. And every one of these gray boxes are also something you have to keep on running. So these are highly available. So you need to manage 2 of them, or if not more, right? So this can be somewhat simple and easy, if you're using an orchestration tool and if you're running on a single stack. And one of my favorite stacks is, of course, Spring and Spring Boot, because I'm a Java developer. They make this very, very simple and easy to do. I think that for the most people, though, the problem arises when you are not on a single stack. Just a quick question to everyone here. How many people here are in an organization where you only use a single stack for all of your services in application? Yeah, one person. Yeah, very lucky. But I guess the rest of you, right? Most of the people don't. You have more than two, more than two, more than two. Yeah, more than five, maybe. Yeah, some people have more than five, right? So what happened then is for every one of the stack that you are dealing with, you have to go back and figure out how do you deal with all of these cross-cutting concerns. Do I do proxy? Do I do client-side load balancing? How do I do fault tolerance? How do I do observability? And for every one of those stack or languages, you have to go and find potentially the similar solutions that Java has, and then maybe you need to find similar solutions for your stack as well, or for that language. Maybe you're using not just Spring and Spring Boot. Maybe you're using more than one framework. Maybe you're using Java and Node and Go and PHP and Python, whatever. And this becomes ever so difficult if you want to have all of these things work nicely in your microservices architecture. Now, at the end of the day, though, I think that as developers like myself, all I really want to care about is that, well, first of all, I want to make sure that the cross-cutting concerns are taken care of. But if I'm just making a call to a service, it should be as easy as just making a HTTP call, right, or a gRPC call, or a HTTP2 call to the target service. And hopefully, those concerns will be also taken care of. But that's the programming model that we have today, except that all of these components are really just added into your client libraries. So this is where Istio comes in, or a service mesh, so you will call it. Basically, at the very high level, this is the way I can think about this. When you're running your microservices in a service mesh, every request you make is going to flow through the fabric of the mesh. I know it sounds very abstract, and it almost feels like I'm talking about, we're moving in the fabric of space-time. But this will be clarified in a second, and we'll understand exactly how this works, right? So Istio, if you think about this, and if you compare it to Kubernetes, right? Kubernetes was designed to run and manage your containers through well-defined APIs and terminologies, and that can make them become reality. Now, Istio is designed to manage your service-to-service communication through some well-defined terminologies as well. And you can write a configuration file for Istio to define what it is, how it is that you want the services to communicate. And then Istio will make that and become a reality. And it's an open source project that was open source originally by Google, IBM, and Lyft. And it was designed to run in different environments, including Kubernetes, but also beyond and outside of Kubernetes. It's just that for the first version, they really just focused on running this on Kubernetes first. But this can actually work in environments outside of Kubernetes as well. Now, if you think about Kubernetes and the way that it works, right? You have the well-defined API, you push it into Kubernetes. That is what we call the control plane. A control plane then will take that configuration and create a reality. That is what we call the data plane, or the serving plane, or the data path, right? So if you want a load balancer, you write the definition, you send it to the control plane, and we will create a physical load balancer that becomes the data path. And for that reason, if the control plane goes down, the data path will still be there. It just you lose control on how to manage this data path until the control plane comes out. So Istio is then the control plane for service-to-service communication. And the way that we can do it is by allowing you to write, rather than writing the deployment descriptors, we can allow you to write routing descriptors or circuit breaking descriptors. And then through the control plane, we'll configure your applications to behave in those ways that you want, that you have in your configuration. And the way that we're doing this is a couple of steps. Well, number one is that rather than having some of these client-side libraries that you include in your application, we push all of these logic into a dedicated proxy that's specific to your service. Okay? So all of these circuit breaking rules, the client-side load balancers, potentially the ability to push traces to your tracers, all of these logic can be pushed into a dedicated proxy. So we take that away from your application client libraries, and we push it to a separate component called the proxy. And this proxy is based on a C++ proxy that was originally written by Lyft. Right? It doesn't make a lot of sense to take away 80 megabytes of jar and give you a 300 megabytes ESB. So this is actually a very small proxy right? So we're taking away some of the jars and we're pushing it into a proxy. And this is a small proxy that's made to be very efficient, and it's also battle tested in a production environment. And this proxy can do a lot of things for you, right? The things that we thought about to add into our client-side application, this proxy can actually do all of those things. So this proxy can load balance for you. This proxy can do TLS termination. This proxy can handle circuit breaking and health checks and so on and so forth. Now, some of these might sound a little, like if I were to think about the old days in service-oriented architecture, some of these things might sound like an ESB, right? Enterprise Service Bus. But I can guarantee you that that's not the case, right? Because that would be a little scary, right? In an ESB, the problem is that they also promise to handle a lot of these things and also routing and all of these things that you can apply to the ESB. But in a traditional ESB deployment, you have a single or a couple of ESB instances, and all the traffic is routed to that. And the ESBs all of a sudden become a bottleneck for your entire SOA deployment. Now, the way that Istio works is that we actually deploy a proxy instance for every one of your microservice instances. What that means is that rather than having 1 or 2 proxies, if you have 1,000 microservices, you get 1,000 proxy in the typical default deployment. So every one of your microservice instances will have a proxy running right alongside of it. And the way that we're doing this is by using the sidecar pattern that we kind of introduced in Kubernetes through the concept of a pod. So basically, we can run your application container and then attach a sidecar container right next to it. And together, they are known as a pod. And this is the single unit that Kubernetes can schedule onto the same physical resource. So when you run a sidecar container inside the pod, well, what that means is that we're guaranteed to schedule this proxy right next to your application, your service, on the same physical resource, sharing the same network interface, and also sharing the same value amounts if you want. And what that also means is that when the microservice A makes the call to the proxy, it's actually done through a local channel. It's actually not going to go over the physical network. It's just going to be somewhat optimized by the kernel, so it's going to be routed directly to the proxy through the local networks, okay? And so what that also means is that when we deploy this in Kubernetes, the descriptors that we write, we can push it to Kubernetes, and then remember about the control loop and how the controller takes the descriptors and make that into a reality. The way that we configure these proxies is by, again, writing these YAML files, potentially, and then pushing into Kubernetes. And the controller is known as the Istio pilot, and pilot will read this configuration and then propagate the configuration to the proxies the way that the proxies can understand, okay? And for that reason, the proxies are also interchangeable. Today, we're using Envoy by default. It's also possible potentially to use other proxies as well, right? Because Istio pilot is the one that will translate the configuration that we have and then pushing it down to the configuration that every one of these proxies will understand. And then rather than using some additional server discovery mechanisms or centralized configuration mechanism, if you're running inside of Kubernetes, then some of the mechanisms are already provided by the Kubernetes environment already. So for serverless registry, we can just use Kubernetes servers. For configuration, we can just use Kubernetes config map. And that will somehow simplify your environment quite a bit. So the way that this actually works is like this. So remember, we deploy a proxy instance for every one of your microservices. And they are all centrally managed by the Istio pilot. So Istio pilot will propagate the configuration to every one of these proxies. However, one of the things that we do is that when you make a call from microservice A to B, for example, we will seamlessly intercept this request by using IP table rules. We'll seamlessly intercept all of the connections. And so naturally, the connection to service B will be intercepted by the proxy, and the proxy will examine this payload, and then it's going to say, oh, so for this request, you want to talk to service B, and the proxy would understand where all the backends are, and the proxy will then make the decision on how to load balance based on your configuration, and then it's going to pick one of the backend and route the traffic to that backend. And the backend that received this request, of course, the incoming connection will also be intercepted by the proxy as well. And at this point, proxy can decide whether servers can actually make the call. So the proxy can do some policy checks to make sure that this call can actually happen. And then if it can, the proxy will then forward the request to the actual instance on the back end. And that is how it all works in this fabric, right? So every request will be captured and processed by the proxy in this case. And then we can do very, very interesting things. Now, if you are a Java developer, you probably know the concept of AOP, aspect-oriented programming. That is how we used to deal with dealing with cross-cutting concerns. We'll wrap some common logic across all of the methods that do the similar things. Now, this, Matt Rabel once called it the AOP for microservices, or basically wrapping and capturing the requests and filtering them through before we passing it along to the backend. Okay? Now, if the proxy knows about everything that's happening, then we can start to ask interesting questions. Who is actually talking to me? Well, the proxy knows, because the proxy knows who made the call, and the proxy knows who the call was routed to. How long did that request take? Well, the proxy has received the request, the original request. The proxy knows when the response came back, so the proxy knows the latency. And that can be exposed through Prometheus, and then it can be captured and shared and analyzed. If you need to know, if you need to have an entire chain of the calls to be traced, well, if you pass along the right headers, the proxy can capture these traces and propagate that to the trace store, like Zipkin or Jaeger. But one of the most important ones for me is that through the proxy, through this communication mechanism, the ones that's here locally, right, they can be plain HTTP. But when you go over the wire, over on trusted network, that is where you may actually want to encrypt your communication. And if you were to do it by yourself, that may be very difficult to provide a mutual TLS library or whatever, like dealing this with yourself between services. Through the use of Istio, we can actually provide mutual TLS connections seamlessly between your services, because when you talk from A to B, from your application perspective, it's really just a regular HTTP call. But through the proxy, they can actually be configured with mutual TLS through a centralized certificate authority, so that they can exchange the certificate and they can negotiate that mutual TLS connection. And you can do all of these things seamlessly. And that is really the magic behind the scenes in a Istio service mesh. Now, how does this all work? I'm just going to do a very quick demo. And I've been thinking through, like, how do I demo this best? I want to write something that's most simple, most basic, with no magic whatsoever. I'm not going to add any additional client libraries behind the scenes. And of course, I can do this in PHP or Go or Node, but I don't know any of those languages well. So that's going to be an issue for me. So I'm going to write it in Java. Okay, I'm going to use the most basic Java libraries that we can think of. And then I'm thinking about writing two services. So I thought, oh, maybe I can write a work service. So I'm going to have a work server. And then I think about, what is work? Work could just be a series of meaningless meetings every day. And so for that reason, I'm going to write a meeting service as well. Okay, so what it is that we're going to write is a work server that will call meeting server a couple of times. Okay? Now, I'm going to use the most basic stuff here that you should probably never use. I'm going to use the Tsang HTTP server in the JDK, which probably is not production ready, so don't use it if you want to try this out. So do it in some other service if you want, but this is pretty easy to do. So I'm going to write a new server here. I'm going to say server is equal to HTTP server. I'm going to create a new server here. I'm going to listen on port 8081, and then I need to give it a backlog here, and that's it. And then I can go ahead and start the server also. And then the server will have to handle some requests here, and it's going to take in an exchange like that. And the exchange is where we can send data back and stuff like that. Now, I don't know about you in terms of what you do in a meeting. This is what I do usually. There you go. Right? Yeah, there we go. And of course, it's going to be some exception here. Let me see here, surround. Again, I don't know what you do with the exceptions. This is what I do usually, do nothing. There we go. And then I can go ahead and send back that if I successfully slept through my meeting without getting fired, I'm going to send back 200 OK. Yeah, everything's good. And then I'm going to close this connection, and that's it. Right? That is a very simple server that I can write. I'm going to go ahead and try to run it. How many people think this will just work? Nobody. Wow. That's a tough crowd. All right, so I just started this application, and it seems like it's working. Let me go ahead and make the request. I'm going to say curl localhost 8081 and meet. And of course, it doesn't return anything, but I should be able to see that this little handler is slept through 215 milliseconds, which is not too bad. And then we just need to go ahead and do this on the work side, which I'm going to make a couple of codes. Now, because of the time, I'm going to cheat a little bit. I'm going to just make code appear magically. All right, so number one, we need to create a HTTP client. And this client is going to, it has to be a HTTP 1.1 client. If you try to make a call in the service mesh with HTTP 1.0, it's probably not going to work. So make sure it's HTTP 1.1. And then we're going to, let me see here, make the builder with a new request. And for this one, we're going to use an endpoint, which is configurable on the top. So here, we're just going to be calling HTTP and then calling the endpoint/meet. And then we're going to call the meeting method 4 times. So I'm going to route it 4 times. And then for each time, I'm going to send a request. And then if I get the 200 response, I'm going to say meeting plus plus. I'm going to count the number of times that I successfully went to the meeting and slept without getting fired. And then I'm going to, here's the most important part in the whole Istio thing, if you want distributed tracing. That is that in Istio, you have to propagate the headers if you want to trace across your requests. And there are a number of headers you have to propagate. So your application is responsible for receiving the headers that will be generated by Istio. So these are the headers, the XB3 headers. That's the standard ones. And then you also need to get some of the additional one, like OT span context and X request ID. You need to capture these headers. So if these headers don't exist, Istio will generate it for you. If it does exist, then you do need to propagate it down. So in this case, what we're doing is to basically iterate through the header, making sure that if it's actually there, I'm going to set the header and propagating it to the next request. Okay? And that is really all I'm going to do. And then I'm going to go ahead and run this work server as well. And let's see if that actually will work. So this is up and running. And I'm going to just go curl localhost 8080 and /work. And hopefully, if that works, we can see that we made the call to the backend 4 times and 250 milliseconds each. So 4 times, that's about a second in total. And we can see that this actually works. However, if I actually go ahead and stop the backend, now if I make the call, the error kind of propagated back all the way back up to my to the very first service, right? Because there's no circuit breaking here. There's no magic. Of course, if the connection doesn't work, it doesn't work. But we're going to deploy this same application into the Istio environment through Kubernetes right now, okay? The way I'm going to do it is by just basically, I'm going to compile it, clean, compile, and I'm going to build a container. And by building a container, I'm going to use this little tool called Jib, J-I-B. This is a open source project from Google. Who did it go? There it is. So by using Jib, I can actually build a container without Docker installed locally on my machine, and this will push this container image directly to the registry. And it's done, right? So basically what I'm doing is I'm compiling the classes, and then I just create the container through Jib, and it's pushed directly to the registry in here, right? So that's on my Docker hub right now, okay? And I'm going to do the same thing for my work server, so just make sure I don't cheat. I'm going to clean it, I'm going to compile it, and I'm going to Jib build. Now, just to show you how small this application is, I'm going to package it up to a jar file, just so you can see what that looks like. So this little microservice that has no magic behind it we created this jar file, and this jar file is only about 3.3K, right? Rather than tens of megabytes to do something pretty simple, it's really, really small because we're just using out-of-the-box functionality from the JDK. And similarly, for the work server that's done, I push everything to Kubernetes. Now, the way I'm going to deploy it into Kubernetes is, of course, by using the well-defined APIs that Kubernetes offers. And in this case, for example, if I want to deploy the work image, this is what I'm going to do. I'm going to deploy 2 instances of my work image. And the name of the image is here, right? So that's the name of the image here, which I just created. And I'm going to configure the endpoint so that it can use Kubernetes service discovery out of the box. Basically, all I need to do is to say, call the meeting server, because I'm going to define a meeting service, right? And then in the service here, let me see here, meeting SVC. right? So for example, for the meeting server, I can define the service. This is a service kind right here. And this will, behind the scenes, create a load balancer for me. It will listen on port 8081. It will route to my target port 8081. And then it will route to the backend by using the labels. So I'm just going to go ahead and deploy the whole thing. Let me make sure I'm connected to my Kubernetes cluster. Now, in order for Istio to take place, remember, we somehow need to get the proxy deployed alongside of my microservice. Now, if you notice that in this particular deployment descriptor, in the containers, I only have one container, right? So there's the container I have, which is the work server, and that's the container I'm going to run. How does the proxy actually get in there? Well, to do that, you have two ways. One is by injecting the proxy manually. So there's a little utility called Istio CTL, and from here you can do a kube inject. You can give it a file that is a Kubernetes deployment, and then if I look at what this filter does, is that it will filter through your existing descriptors, and then it will keep all of the existing configurations. Like here, we have the image, the endpoint names. But if I scroll down a little bit, this filter will inject a second container inside of the same pod, and that will be the proxy container that all the traffic will be routed through. Okay? And if I scroll down even a little bit more, what we're going to see is this thing called the initialization container, which is right here. And this container will be started way before either of the previous two containers will start. So your application and the proxy will start only after this container is started successfully. And the init container here is going to configure the IP table rules. What this will do is to basically configure a rule that will redirect all the connections to the proxy port 15,001. Okay? And that is how we can inject the proxy and intercept all the traffic as the requests are flowing through. Now, another way of doing this is by using what we call automatic injection. So I have configured my Kubernetes cluster so that there's what we call a mutating admission webhook in Kubernetes. Basically, anything that we deploy into this environment, if I'm deploying it into a namespace or with certain labels enabled, the webhook will take effect. What that means is that Kubernetes will intercept potentially the deployment of my application, and then it will run through the kube inject locally. It will run through the kube inject on the server side, and then generate, producing a new descriptor and updating my configuration as I'm deploying it. Okay? So I'm going to show how that works. I already have this configured. So I'm just going to go ahead and deploy this whole thing. So I'm going to deploy both the work and the meeting server behind the scenes. Right? And now if I go ahead, remember in the YAML file, I only have one container. But if I go and see the status of this deployment, we can actually see that there are two containers running. That is because my environment has been set up with automatic injection, so we automatically injected the Istio proxies behind the scenes for every one of these microservice instances. So that's why every one of these instances have two containers. One of them is the application, the other one is the proxy, and of course the initialization container also ran, and so this is all being set up properly. And of course, I can go ahead and check out if I can connect to it. So for that, I'm going to get into the shell that is inside the cluster. And then maybe I can make a call. And through Kubernetes native service discovery, I can use the DNS name called work server. And port 8080, that's the way I define my service. I'm going to call work. And hopefully this will work. And, oh, whew, thank goodness. Yeah, it was a little slow the first time, but it worked. Yeah, not bad. And we can see that this is working pretty well, right? So this is just going through the environment. However, at this very moment, this is already running on Istio. This is every request I'm making at this very moment is already intercepted by the Istio proxies. And you can see how transparent this is when I'm making this call. Even the shell right now is intercepted by Istio too. What that also means is that now I can use the well-defined terminologies that Istio provides me through the idea of a custom resource definition. I can do interesting things. So for example, if I want to expose the work service on the public internet, I can route it through the Istio ingress gateway. And in order for that to happen, I need to define a new gateway. I need to bind the gateway to a host name. So here I'm binding to star. That means I'm going to listen to every single host name that comes through the IP address. But imagine if you have virtual hosting where you do have different host names, you can route the different host names to the same IP, to the same ingress, and Istio can route the traffic based on these virtual host names as well. And we're going to define that we're going to listen on port 80 as well. So I'm going to go ahead and apply the gateway. And what this will do is to say, hey, Istio, I want to listen to traffic on your public IP address. Okay? And then the second thing that we can do is that we can define these things called virtual service. A virtual service in Istio terminology is really just a way for you to define what you want to do, how you want to route your traffic. Okay? So in this particular case, I'm going to define a new virtual service that is called the work server. And we're going to say any request that comes in on /work, I'm going to route to the work server backends that are already deployed. And because I want this to be exposed on the public-facing ingress, I'm also going to bind it to the gateway that I just created. Right? If I don't bind it to the gateway, the virtual service is all internal. But if I bind it to the gateway, then it becomes public. So let me go ahead and try this. I'm going to bind this to the gateway, and I'm going to apply this configuration. Now remember how this works. I apply the configuration. I send it to Kubernetes. Istio pilot gets this configuration, understands what it is that you want in the desired state, and then goes back and configures the proxy accordingly. Okay? So then all of these configuration will be applied. And because of that, I should be able to make the curl request to my gateway. So let me go ahead and try that. Let me see if I can find my curl to the IP. No, I can't. So let me go ahead and find the IP address here. So this is actually a service that's in the Istio system. Oh, let me see here. Get SVC. And there will be an IP address that's associated with the Istio ingress gateway, which is that one. And the IP address is that. So what I can do then is I can do a curl that, and then work. Now remember, this goes through the ingress gateway, goes to the virtual service definition where we're capturing the /work URI, we're matching on the URI, and then forward it to the work service, and now it's routed to the work server, and then the work server actually called the meeting server 4 times, right? And that is what happened behind the scenes. Now I'm going to put this into a while loop. That's the same IP, right? Yeah. I'm going to put this into a while loop so you can see what happens then. So here we go. So this is a while loop. You can see that I'm attending 4 meetings right now, right? Then we can do interesting things. So for example, if I want to introduce a chaos monkey, in this case, because I want to have fun, and if I want to basically test the resiliency of my application, or if I just want to have fun, I can tell Istio, I can write a configuration here for my virtual service. Here, remember, this is how we decide how to route. So in this case, I'm going to say anything that's being routed to meeting server, I want to fail it 100% of the time. Okay? This is just for fun. And remember how this works again. As soon as you apply this configuration, Istio pilot picks it up, right? And we configure all the proxies. And now, very quickly, the proxy takes the configuration, and now all the request to the meeting server is now failing with the 503, right? And you'd be like, that was funny, like, we're trying to work, let's get rid of it, right? Then you can say, well, let me get rid of this rule, and it comes back, right? It's that simple. And with the same mechanism, this is what we can do. We can actually deploy 2 versions of my service. So what I'm going to do is to deploy a second version of my work service. Let me see here, v2. I'm going to apply the second version. And the second version of the work is basically when I work really, really hard. There we go. Uh-oh. Did I not deploy something properly? There we go. Aha. So this is where I'm working really, really hard. So when I'm working hard, I go to 8 meetings. When I'm not working so hard, I only go to 4. Okay? So you can see how this is being load balanced across the different services. And you can also see that it's a little bit deterministic. That is also because, by default, we are using round-robin load balancer. However, it's also possible for us to get a route to traffic through Istio. What that means is that I can define the destination rule here so that we can capture the 2 different versions that I just deployed. For my work server, I got 2 versions, and I have v1 and v2. And I need a way to define what these 2 versions are by using the labels in Kubernetes. So I can use the version label here. So I can say v1 means version is equal to latest, and v2 means version is equal to v2. Now, of course, you can also use blue and green You can say old and new. It doesn't matter. It's just a way for you to name your versions your own way. So I'm going to go ahead and apply this v1, v2 definition so that now I have two different versions to work with. And now what I can also do is to say, OK, I tell you what. I like to start off with all the workload routed to v1. So I can go back to the virtual service. I can define the matching rules here, which we can match on URI and headers. But then we can also say route all the traffic to v1 and no traffic to v2. And all I need to do is to apply this through Istio, and we can actually do traffic routing for you. And you can use this very same mechanism to do blue and green deployments, or you can use it for a canary, new versions as well, by shifting the traffic to the percentages that you are looking for. So now we can see very effectively we shifted all the traffic to v1. And we can use the same thing to shift the traffic to v2. Now, with all that said, right, routing is just one small aspect of Istio. What we can also do, of course, is to set up retry rules and circuit breaking rules as well. So for example, if you want to set up a retry rule, rather than updating your application logic, the proxy can handle that for you. So we can just set up the retry rule like that to say, let's retry 3 times for my meeting service in case that it goes down. And we can go ahead and just update that. And the proxy will be configured appropriately. Okay? Now, just remember, this application has absolutely no magic except to propagate the headers. And what that also means is that through Istio, we actually get quite a few things. Number one, we have a Grafana dashboard that's being installed by default. And I can actually go to this dashboard right now. And what we can see is actually the traffic latency and also the successful requests that is actually captured by the Envoy proxy. So I can go ahead and go to the dashboard. This is pre-created. Let me go ahead and find the work server right here. And we can see the QPS that is being routed through the Istio proxy right now. And we can see the success rates of that. Now, of course, if I go to the meeting service, let me see if I find it here, meeting server. Right? We can see very clearly this was when I failed the request 100% of the time. You can see that failures in my graph as well. So that's pretty cool. This is, by the way, out of the box. Now, if I need to see a whole distributed tracing across like exactly who is actually making the call, what I can do is to open up the Jaeger console here. So I'm going to open up 16 that port there. And I'm going to go ahead and go to my local host here just to see the Jaeger console. And then what I can do is let me see the ingress gateway, because that's where the traffic are routed to. And then let me go ahead and find the traffic. And you can see all the requests that comes in to start work. And because we're propagating the trace headers, we are also capturing all the traces. So here we can very clearly see the work server calling the meeting servers a number of times, and each one of them with its own latency. That's all being done out of the box with the Istio installation, assuming you're propagating the right headers, right? And the beauty of this whole thing is that if I were to deploy this with mutual TLS connections, so that my connections here are secured between work server and meeting server, it's really exactly the same thing. I do not need to modify my application. Maybe slight changes in the way I deploy it, but without changing anything on my app, this communication can actually be secured via mutual TLS as well. Okay? So there's a lot more things we can do. And one of the most important one that I want to mention is that not only do we allow you a control plane to control the routing of your traffic by shifting traffic, mirroring traffic, and all that, and adding circuit breakers, all of these metrics that we're collecting, or the traces that we're collecting, these become platform services that can be somewhat abstracted away by Istio as well. And by that manner, what we can also do, just like Kubernetes abstract away your underlying infrastructure, here we can also abstract away the way that you're collecting your metrics. And we can actually forward these metrics and traces onto cloud-specific managed services, so you don't have to manage your own. Okay? With that being said, let me see the time. Yeah. Just remember, Istio is a pretty neat tool that you can apply in your Kubernetes cluster today. You can also run it outside of the cluster as well. And then you can get visibility, resiliency, and you can control your traffic all through the same control plane through Istio. Okay? And if you have any questions, please join the community. You can participate in the email groups on Istio-users. You can join Istio.io. You know, just we are here because we want people to try it out. It's version 1.0 right now, and we would look forward to your feedback when you're trying these things out. And if you have any questions, you can find me on Twitter and on my website. And with that, thank you very much for your time. Thank you.